Thanks a lot, Mike. It's really a pleasure for me to be here. As Mike said, my name is Ashok Srivastava, and I'd like to give you a little bit of an overview of my talk and some of the items that I'm going to be covering. So, as he mentioned, I've had the luck of being in a variety of different application domains, including the earth sciences, the space sciences, aeronautics, space systems, all of that at NASA. All the while, though, I've been involved in the business world in various capacities, working with startups and other companies. When I came to Verizon, one of the key challenges was to build an organization, a new organization that focused on large-scale, what I call large-scale machine learning. They say big data and analytics. And so I'm going to be taking you through a blend of different application areas and also talking to you a little bit about the machine learning algorithms that we're developing. So I started at Verizon about a year ago, and as we're developing the new application areas and the new topics of research and development, what we're finding is that, what I'm finding at least, is that there's a very nice transition of some of the technologies and some of the methods that we developed previously at NASA into Verizon. And it's not too surprising to me, and I'm sure not too surprising to you all, to see that similar algorithms can be applied in very different contexts, and it's something I've always been interested in. I would invite you to ask questions as I go through my presentation. Let me know if you need any clarification. I can go into as much detail as you'd like on any point that I'm making, and I can also have discussions after the talk. So really, it's a pleasure for me to be here. I want to thank Mike and all the organizers for having me here at MMDS in 2014. So as I mentioned, very different worlds at the high level, right? NASA is kind of focused on aeronautics, space systems, earth sciences, space sciences, and so forth. Verizon, a huge phone company, almost a conglomerate of entities that are running massive networks worldwide. But there's something in common and something unique also about these two organizations. They both have enormous data volumes. They both have massive computing infrastructures, although they're quite different. At NASA, the kinds of computing that we did and what we're seeing at Verizon are different, and I'll be touching on that a little bit. And we hope, certainly at NASA, we felt that the work that we were doing had significant public value and significant value to society at large, not only within the United States, but abroad. And we also hope that there will be a similar effect at Verizon. So let me start off very high level, kind of giving you a motivation of why a company like Verizon would be interested in starting a new team focused on big data. So as you all know, Verizon is a huge phone company. It operates in about 100 million, with about 100 million subscribers across the US. It operates about 2/3 of the world's internet backbone. It operates private networks. It also operates wired networks, so-called. These are networks that actually power cable TV and other kinds of broadband services around the US. So it's a huge company from that regard. Why is it that they would be interested in starting something in machine learning, big data, and analytics? Well, this is one of the key drivers. If you do a survey of business leaders within the US, not just at Verizon, but at other places, you'll find that about 1 in 3 are making decisions and they don't really have the information needed to make those decisions. And in a place like Verizon, where there's so much data, there's a question, is it possible to give those people at the helm of the company more insight into what's going on in their businesses? And so this is something that a lot of people have thought about and worked on. Given the context, though, of the data set sizes that we're dealing with, and this is something our marketing department has put together to give you an idea of the size and scope of the data that is coming just in the US on mobile devices. So the smartphone penetration rate is going to go up to about 80% in 2017. About 74% of people are going to be doing gaming. 45% will watch TV and video and so forth. And another interesting statistic, about 21% of 2013 Black Friday e-commerce activities happened on mobile devices. So clearly, the world is moving towards a mobile device-centric situation. Now, all of that data comes in, those that are on Verizon subscribers, All of that data comes into the network, obviously, and it's recorded. But we have to deal with privacy policies, which I'll get into in a little bit. But even given those privacy policies, the amount of data that we're dealing with is really extraordinary. There's about a 40 to 45% growth projected per year. So again, going back to the notion of running a business or making decisions on this data, the data set sizes that we're dealing with are on the order of 12 petabytes a day. And that excludes the data that's actually the payload on the network. So for instance, if you watched a Netflix movie on your Verizon device, that 1 gigabyte file is not included in the 12 petabytes per day. So this is the intercommunication in the network that's generating about that much data. So given that much data, how you make decisions and how you do it in closer to real time is really a challenge. And I'm going to be talking to you a little bit about that and also some of the application areas that we're dealing with. Obviously, the company wants to generate revenue from this data. And I've given kind of a picture of how people are thinking about revenue generation within a company like this. And I suspect within a lot of what I would call older companies, more established companies, this kind of a flow is very typical. I'd contrast that, though, against companies which are working more at the startup level. I don't think they would necessarily think of things in this way. I think they would think of things more in the terms of solving specific point problems and applications. But when you're in a large enterprise like Verizon or IBM or companies of that scale, revenue generation takes on a whole new meaning. And so at the bottom of the stack, we have analytical reports. This is what you all would say could be easily computed using SQL queries or the like. These are visualizations that humans can read and take action on. And that's usually at the lower end of the value spectrum. Between that, we have discovery systems, which, as you know, are based on machine learning. These can have a SaaS model, a software as a service model of revenue development. And then finally, predictive methods, which can be real-time, and many of the applications we're developing are real-time. These are certainly based on machine learning and other statistical methods, and these are often of the SaaS world, the software as a service world with shared revenue. And as you can see, we've labeled the right-hand axis going up as increasing revenue. Again, to give you an idea of what we're trying to accomplish here in our business setting, in many cases, what you find is that it's possible to take a big data and analytics application or a machine learning application and monetize it to the tune of between $20 and $100 million. And you can see many, many companies in Silicon Valley and in other places that are doing that. At Verizon, the scales are a little bit different. Here, the idea is that we need to create technologies that would be generating on the order of several $100 million or more, maybe even $1 billion of revenue in the next couple of years. And to do that requires a different kind of business model. It requires a business model which shows scale, but also shows a great deal of connection to the subscriber base or to the basic businesses that the company is operating, right? And so that puts a different challenge on us compared to a smaller startup. And that's something that's been pretty interesting to think about from the business side of things. So the way we're doing this is building a cluster. We call it Orion, and it has the following very high-level architecture. So at the bottom, we have a lot of data coming in from the Verizon network. So this would include the wireless network data, which essentially includes clickstream data. That's the log of what people are looking at on their mobile devices. Location data, in other words, where a person is at a certain time when they're making, let's say, a phone call or making a text message, and then the time at which all of those occur. And that's one key aspect of the data that we're dealing with. Another data set is what we call PIP data. This is private internet data. Essentially, when a large company like Citibank, let's say, is operating a network, that network actually might be managed and run by Verizon. And so all of that data is available. Other enterprise data, so CRM data, data from other sources, a lot of this is structured, and frankly, a lot of it is unstructured as well. Fios data, so this is the fiber optic data that's going into about 6 million homes within the US. All of that data is, in theory, available. Third-party data, so weather data, traffic data. We have traffic data, and I'll tell you a little bit about that, but there are other data sources that are available, and then publicly available data. So all of this is at the bottom layer of the stack, and on top of that is a big data infrastructure. As you'd expect, we're running a large, we will be running a large Hadoop ecosystem, also massive parallel processing, traditional relational databases, NoSQL databases, and building a good deal on Apache products. On top of that is the traditional BI and reporting dashboard. So these are the visualizations that we're talking about. But on the right-hand side, you can see recommendation engines, insight discovery, prediction algorithms, and so forth. And that's really what some of the focus of my talk is going to be today. The vertical solutions that we're focusing on include a wide variety of applications. Advertising, as you might expect, is one of the key areas that we're working with. So this would be mobile advertising. This would include online advertising. It could also include advertising to point-of-sale systems, to video and TV systems as well. So it's a broad spectrum of advertising, and one of the key challenges there is to take the data that's at the bottom of this layer and utilize it in order to do targeted advertising. But that's not the only activity that we could do. We have a large organization dealing with cybersecurity issues. So remember, looking at what's happening on the worldwide network and trying to understand and look for threats and mitigate those threats is actually a major challenge for a sister team of mine. Network health management, so the idea of taking the data off of the network and doing predictions on when there might be network congestion, how to optimize the flow of the network data, and so forth is another area that we're focusing on. M2M, or what we call connected machines or machine to machine, yet another area where we're running on the order of, let's say, more than 1 million devices. It's probably close to 2 million devices right now that are all connected to the network. These are not handsets or phones or anything like that. These are coming from machines like power grid meters and so forth. All of that data is possible for us to analyze. So this is the good news about Orion. It's going to be a large system. It's getting established right now, but unfortunately, this is Orion today. So it's a very large warehouse building in the East Coast. You can see that it's going to be very large, but right now it isn't. It's still under development. And because of that, a lot of what I'm going to be talking to you about is not at the scale of Orion yet. We expect this is going to be completed by the end of the year. So it's not at that scale yet, but it's still at an appreciable scale. I'll also be talking to you about some of the work that I did at NASA, because that's also at scale and I think has a nice tie with what we're talking about today. So let me start with the advertising platform. I've divided the talk into the major application areas that we're focused on, and I'll give you an idea of the way we're thinking about things. So as you know, there's a tremendous onslaught of first-party and third-party information that's available, and all of this is at different levels of personalization, and it can be used at different levels of personalization. It can also be used at different levels of granularity. What I mean by that is that most of the subscribers that Verizon has fall into what's called the opt-out, or the non-opted-out category. So these are people who have not told Verizon about their own privacy interests. So they haven't made any comment, and for those people, which is the vast majority of people, the best that we can do today is what we call aggregate anonymous analysis. So that means that we're not allowed to take that data and particularly target an individual. We can only analyze the data in an aggregate anonymous fashion. There are actually a subset of the population, and a growing subset, I should say, who have opted into our marketing programs. And because of that, we are allowed to use their data, their clickstream data, their location data, the time at which different events occur. We're allowed to use that data for specific targeting purposes. And then there's an appreciable size of the population who said, please don't use any of our data for targeting. And for those people, we exclude them early on in the data collection process. And it doesn't come to my team, and we don't deal with it. We're trying to develop an understanding in a business case which is working in this rather complex ad ecosystem. And the reason that I put this up is to show you that when we're thinking about machine learning at Verizon, or frankly, I'm sure at many other companies, it's not just about the point solution of the algorithm. And frankly, that's not why I'm starting off talking about algorithms here. I'm trying to give a big picture because operating in an ecosystem like the ad ecosystem or the M2M ecosystem or the cybersecurity ecosystem is really a non-trivial activity. The machine learning can play an important role there and probably a differentiating role, but it's really not the place that we start off from thinking about how to run a business of this scale. So when you look at this ad ecosystem here, on the left-hand side you've got brands, so these are the people that want to do the advertising like Lexus and IBM and other companies like that. And the right-hand side is the person with the cell phone, right? He or she is the one who's looking at CNN.com, and then at the bottom you see the little banner ad, or maybe there's another kind of interstitial ad that's occurring, or maybe there's an ad insertion on the video that a person is watching. But that's on the right-hand side. And in between, this is a simplified diagram, frankly, of what happens to take an ad from the left-hand side and what happens on the right-hand side. Interestingly enough here, where the machine learning and where a lot of the data analysis occurs can be at the enabler level. And if you look at it, that makes about a nickel out of every dollar that's spent in the ad market. And that's exactly why we need to think bigger than just the data processing, just the targeting, and just the algorithmic design, right? That's why we have to think about a larger business case. And so then the question is, given this kind of a ecosystem, where should a company like Verizon play, and how should data analysis and machine learning fit into these roles? Many of these companies do have a significant data mining or data analysis activity, and many of them don't. They're simply exchanges. But figuring out how we should build that business and how data mining, machine learning, and analytics should fit into that picture is one of the key challenges that I and my team face, along with some other teams within Verizon. So this gives you a high-level overview, again, of how the revenue that is put out by a company like Lexus is split up across all the different players in the ecosystem and how it ends up at the consumer space. So the data that we're using, again, takes app usage data, clickstream, demographics, location, and it could generate a profile as follows for an opted-in individual. So this is a person, fictitious person, who's married, about 30 to 40 years old, living in DC and so forth. And you can see that there's a great deal of specific information about that individual. So this person is interested in tennis and luxury brands and has shopped at Nordstrom.com. All of that is coming out of the clickstream data. But if you think about it, the clickstream data, if you're familiar with it, is just a log of all of the websites that people have seen, right? And one of the key questions is, how do you take that and generate a profile out of it? Now, in the simplest case, what you would do is you'd create a matrix where each row, let's say, is a customer. And then you might have, let's say, 3 million columns. And each column says they visited CNN.com like 5 times, Nordstrom 3 times, et cetera. So you'd fill out this big matrix, and you'd start doing manipulations on this matrix. It's a huge, sparse matrix. And in fact, that's one of the directions that we're headed. But what's really interesting is that that matrix can have very interesting mathematical properties associated with it. And one of those that we're going to be exploiting is the fact that it's sparse, and the fact that it is a non-negative matrix. And so many of you that are thinking about it would say, aha, you know, the right thing to do is to think about non-negative matrix factorization. That's actually one of the key areas that we're working with. We're trying to explore scale and sparsity in order to optimize those kinds of calculations, in order to generate profiles like this. So this profile obviously was typed in by somebody who said, this could be a profile of an individual, let me type it in. When you want to do that across 100 million users at scale instantaneously, then it starts to pose a new challenge that I'll be discussing in a moment. So to give you an idea of how this works, this is real data. You know, earlier this year we ran an ad for, I think this was for NFL, and we found that the good news was we had a 64% higher click-through rate compared to the target, compared to the baseline population. So that sounds great. You look at the actual absolute numbers here, That is, in fact, 0.23% against 0.38% click-through rates. So the click-through rates are very small. But the way you make your money is by taking that essentially and multiplying it by the number of impressions, which can range in the billions, and then you multiply that by, let's say, $1, $1.50, and that gives you $1.50 per 1,000 impressions. That gives you an idea of how much money can be made here. You have to take that and you have to scale it now across a very large number of subscribers. You have to scale it across a large number of campaigns, and then you can make an appreciable amount of money off of it. But from the standpoint of the machine learning, there are a couple of questions that come up here. It's true that click-through rate is, I guess, 64% higher than the baseline, so that's good. But the question is, could it have been higher? Could we have done a better job of improving that click-through rate? Is it possible for us to actually change the population or analyze the population in a better way to reduce the number of uninterested people? That could also improve the click-through rate. Is it possible for us to find more customers? In other words, do better prospecting? And by doing that better prospecting, or what they call lookalike modeling, is it possible for us to increase the overall reach of the campaign? So those are some of the things that we think about in the context of this. But this gives you, I think, a pretty good understanding of what one of the metrics is that we use and what some of the typical numbers are. Now, the direction that we're headed is kind of different than what I think you would expect from a traditional advertising platform. There are some companies that are doing this already. I would call out Rocket Fuel as one of them that's really thinking, I think, about taking the data and using it in an adaptive architecture. Certainly at Verizon, we're thinking of something similar. And those of you in the control field will closely look at this and say, hey, wait, this guy's talking actually about adaptive control techniques. And that, in fact, that's one of the key directions that we're headed here. What we'd like to do is create what I'm calling an optimal advertising campaign. So if I asked you what that would be, that would probably include a couple of things. It would include some method to monitor the data directly as it comes off the network. It would include the ability to adjust based on the data that's coming, based on the real-time responses that people are making. It would include a decision-making component that says, based on every data point that I've observed so far, what are some of the key changes that I should make in my advertising strategy in order to maximize some KPI, some key performance indicator. So that would be a key activity of this system. And then finally, an observed consumer behavior. So we have to have the ability to work with a large audience in order to make sure that we have statistical confidence in the predictions that we're making. So because of that, it puts a certain constraint on the way Orion can run, right? What that means is that Orion cannot simply be a large Hadoop ecosystem. Because if it is, then what that means, all of the data is coming in and it gets kind of crunched through a big MapReduce job. At the end, you get the output of a MapReduce, which, as you know, is essentially an aggregation of the data. And it's very hard to take that and then build something like this. And so because of that, our technology stack is going to include not only that Hadoop ecosystem that I described, but also real-time components. And those real-time components are going to be such that they can link back with the Hadoop ecosystem, but then also drive some of this type of adaptive architectures. One thing I mentioned earlier is that we want to make sure that this can work across different platforms, not just the online or mobile platform, but also the TV, linear TV platform, the video platform that you watch on your handset or on your tablet, and so forth. And that poses a whole new set of challenges on the kind of analysis that we're doing. Now, as I mentioned earlier, one of the key things that we're trying to do is automatically derive profiles of people and automatically derive what you might call segmentations of the internet. And we want to do this as quickly as possible with as little human intervention as possible. And so one of the ways that we're thinking about it, remember that big matrix I told you about, which in theory has 100 million rows and it has, in theory, let's say 3 million columns, and it's a big sparse matrix. One of the key things that we'd be interested in doing is factorizing that matrix. And one area that we're looking at is, for example, non-negative matrix factorization. We're working with Professor Stephen Boyd at Stanford, who is, I'm sure many of you know, is working in the field of convex optimization. One of the things that we're collaborating with him and his students on is new ways of doing these factorizations and also new constraints that we can pose. So one of the simplest constraints that you can pose, since A, as I mentioned already, is a non-negative matrix, so it has zeros in it and it has some ones and twos and threes in it, but it doesn't have any negative numbers. One of the things that we can do is a non-negative matrix factorization. So that would take A, which is that data matrix, and divide it into two new matrices, X and Y, which have lower rank than A, but also have some nice properties. One is that they're positive, and the other thing that we can do is ask that that X and Y matrix have sparsity associated with them as well. So they don't turn into dense matrices once we do the factorization. Now, this is, I think, a very elegant approach. Many people have worked on it. We're certainly not the first ones to work on this kind of a problem. We're interested in taking it to scale. But if you look at this, one of the observations that Boyd made along with his collaborators, and I know that others have made this observation as well, is that those regularizers that I've written on the right-hand side need not be, in this case, they're Frobenius norms. They need not be that way. They could be L1 regularizers. In fact, they could be any regularizer as long as they're convex. The other thing that we've noted is that A and X and Y need not be subtracted, right? It's very convenient to write it this way. I think that's the way standardly it's analyzed. But it need not be written that way. In fact, you could write any loss function there, L, comma, A, comma, X, Y, right? And then do a factorization. And so he and his team are coming up with new ways of analyzing problems like that. You get a wide variety of applications, or algorithms out of it, I should say. So you can get what they call fractional PCA, where fractional in this context means the amount of difference, percent difference you are from the target. Rather than the squared error, you could do that. You could do an L1 loss. You could do the L2 loss that I've shown here. You could do fractional PCA and many, many other loss functions along with different kinds of regularizers on X and Y. And so one of the areas that we're working on at Verizon is building that infrastructure so that we're not forced to use L1 or L2 or Frobenius norm or anything like that. As long as the loss functions and the regularizers have a very generic, certain generic properties, we would be able to analyze the data and get new answers out. And for us, that's actually quite important. Let me give you some context behind that statement. So let's say that we were taking this NMF calculation, and we're going to apply it to identifying profiles of consumers, those 100 million consumers that I mentioned. One of the key issues that occurs there is that if you come up with dense, very large, dense profiles, like kind of the one that I mentioned there, you can imagine it going on and on with a high degree of density. To take action on that particular profile in the context of, let's say, a 10 to 30 millisecond time frame can pose a challenge, right? It can also be difficult to sell to an ad agency, right? Because you remember from the picture that I showed earlier, the ad agencies are really the ones that are controlling the way the money is spent. So you go there and say, good news, I've got this profile. It happens to be 2 million long, and it has a whole bunch of coefficients in it. And given that profile, you can make some ad placements. It's very hard to describe that to an individual. And that's one of the reasons that we're thinking about sparsity so early on in the development of our algorithms. But that's not to say that that's the only way ads can be placed or that's the only way machines can be controlled. Certainly, we can move more into the real-time system where it's more what we call programmatic buying, where, in fact, the agency does not know the nature of the profile. Instead, what they know is that we're building a system to optimize the KPI or some other performance indicator. And all of that would, again, not necessarily require sparsity, but it would certainly benefit from sparsity. So let me stop here and see if there are any questions before I continue on into the next area. Yes, sir? No, we're not building our own. So this infrastructure is from Cloudera. So we're using CDH5. And we have a small cluster, I should have mentioned, we have a small cluster called Helios, and you can probably guess why they're named this way. But Helios is a smaller cluster, and that is operating Cloudera right now also. You ask an important question about open source, and let me take a moment to address this a little bit further. So the base infrastructure, as I mentioned, is coming from Cloudera and other Apache projects. But what we're finding is to do an implementation like this at scale is not something that you can easily find on the open source market. And because of that, we've invested in developing a machine learning team. And in fact, the leader of that team, Hai Shao, is here. You might want to raise your hand. So Hai is leading the team that is developing new algorithms. What we plan to do as we develop these algorithms is open source many of them so that the community can do that. I know that his team is already working on that, and at the Spark Summit that's coming up, I think in the next couple of weeks, we'll be talking about some of the new work that we're doing with regards to problems like this in that area. So we plan to contribute back to the open source community that way, and we plan to use open source technologies as much as possible. As you can imagine, there are many, many vendors that would really like to participate in this ecosystem, and we're in the ecosystem that we're developing, and we're working with them to some degree, but because we want to control the IP and the stack and so forth, we've taken the approach that I just mentioned. Any other questions? So right now, frankly, a lot of it is done through a visualization and through our actual analysis of the data. So we look at it, and we did this early on, and it was actually very interesting. So on a small set of data, Hai's team, I should say, took the data and factored it in this manner and started looking at the profiles that came out. In other words, looking at Y, the Y matrix. And what they discovered, for instance, that people who are visiting target.com, is that a very clear persona came out. And I'll tell you what the persona was. This was an individual, or a set of individuals, that is up at 2 o'clock in the morning. So I see some smiles coming already. Up at 2 o'clock in the morning. They are shopping for clothes for certain members of the family who are young. And they're looking at strollers, and they are looking at baby clothes, and they're looking at baby bottles. I think that was kind of the profile. So now you tell me, who is that person? The person smiling has to answer. So who's that person? A mid-30s mom. I don't know about the age, but yeah, probably that fits exactly right. So it's a mom up at 2 o'clock in the morning, probably the kid's crying, and they say, you know, now's the time, kid's gone to sleep, now's the time for me to go and make a purchase online, and so they go to target.com. That's the nature of the profile that comes out of this. And I'd say, and Hai, correct me if I'm wrong, that came out in the very first blush, the very first analysis of this. And as we do further refinements, I don't even remember if there was the sparsity constraint in that particular analysis. I don't think there was. So, but that's the nature of the profile that can come out, and then many other profiles can come out. But we have to analyze them from the standpoint of the human right now. When we move more towards programmatic buying and so forth, it's going to change a little bit. So now I'm going to talk to you. I'm switching away from advertising because the entire world, at least, is not yet ruled by advertising. There are a few other things going on in this area, and so I'll talk to you about connected machines. So the system and the space is huge, and it's going to get even larger as time goes on. And what's quite amusing is to just look at slides like this. This is the one from Verizon. You look at the one from Cisco and everyone, and you'll see that everyone says an unbelievably large number associated with connected machines and that it's going to grow. And the numbers that they give you are very much in line with their own businesses that they run. So this one says 426 million ways to interact with customers. It's not 425 and not 427. It's actually 426 million ways to interact with customers. If you look at what Cisco says, they say 50 billion new internet connections are going to happen on the Internet of Things and so forth. GE has some huge number. So when I look at these numbers, I say, yeah, it's going to be big, and we should probably do something in it. But the question is, what should we do in this context? So many things can be done. You know, we're looking at healthcare, energy, transportation. I'll be talking about that one a little bit. You could be talking about manufacturing, finance, and so forth. To give you an idea, there's so much interest in this area that a delegation from Singapore recently came to visit us to learn about how they can apply big data analytics, machine learning, and so forth to help improve manufacturing in Singapore. Now, Turns out that Verizon is running a very large telematics program within the company. So what telematics means is that you can take data from a consumer device that's mounted inside the, I think it's the next picture. Let me just skip ahead. Oh no, I take that back. I thought I inserted this slide here. But there's essentially a small device about this size that you can mount underneath your car dashboard, and that starts to telemeter data to Verizon, and it comes into our systems, and we can start analyzing it. And that is what happened about 2012 timeframe, and you can see that since then we've been making further and further strides into now the airspace and maritime space as well. So a lot of things are happening in this area from data that's transmitted from different devices. I'm going to focus on transportation systems for a few moments here. So when you get data from a car, think about it. You can imagine getting streaming data, let's say about a few hundred parameters coming in on a daily basis. We have about 2 million cars, so far as I recall. Don't quote me on that number, I might be wrong, but I think it's about 2 million cars operating in the US. All of that data is coming into our system. We just passed 1.3 billion miles of data collected. And now the question is, what can you do with that data in order to understand driver behavior, traffic behavior, and so forth? So location analytics becomes very, very important. Comparative analytics across different makes and models, and I'll show you some results of that that's quite interesting. Prognostics and diagnostics about the car also becomes of interest. But then when you take that, match it with consumer data, which, as you recall, we have a lot of that, you start looking at driver behavior, and that becomes very interesting. So let me pause for a moment here and talk to you about why I'm particularly interested in driver behavior. So as you all know, there's a huge rush these days to build more autonomous vehicles, right? That poses tremendously interesting problems for machine learning, for statistics, for sensing, for pretty much all aspects of transportation technology, many aspects of machine learning and so forth. So a tremendous interest there. But one of the key issues that's going to arise that we actually saw at NASA arising in the national airspace is that as there's an increased level of automation, there's also a decreased level of what? More automation means less human interest, human understanding, and human appreciation for what's going on, right? So the classic example is in 1940, apparently GM had this idea. They had this minivan concept, and they had the family sitting around, I think, playing Parcheesi or whatever was popular in the 50s back then, and the car was just driving itself. And you could easily imagine that happening on 101, right? Maybe they won't be playing Parcheesi, but they'll be typing on their smartphones and checking the email and so forth. And because of that, the lack of attention puts a great deal of challenge on the automation that's coming up. And so what we have right now is the opportunity to understand driver attention and the way that connects with autonomous systems or semi-autonomous systems. And I'll talk to you a little bit more about this because it's very, very important, at least in my perspective. Third area you could do is tie now environmental information. And so now you've got traffic, weather, emergency services, and everything. This becomes quite interesting because you can start to look at weather data combined with traffic data, combined with consumer behavior, and get a very different view of what's going on the roads within the US. Now, if you start to look at it more from the standpoint of analytics, these are some of the areas that we're looking at. Anomaly detection, diagnostics, predictions, time series analysis, optimization, and so forth. And so let me go into a little bit of this in some detail. So we think of the anomaly detection capability as one in a series of a cascade of events that could occur on a car or in a centralized system. And really, I'd suggest that we abstract away from a specific car and think about collections of cars, collections of vehicles, collections of devices, maybe mixed types of vehicles. So there could be cars on roads, there could be UAVs, unmanned aerial vehicles, there could be airplanes, there could be other kinds of autonomous systems all working together. Now the question is, how do you build an anomaly detection system in that context? If you do that, what you'd essentially be doing is building an algorithm that can detect a key difference between what's being observed right now and what's been observed before, right? And when you do that, it doesn't necessarily mean that that anomaly is relevant or interesting or actionable or operationally significant. So the second thing that we need to do is figure out what's happening, what the root cause of that problem is. So we're developing diagnostic algorithms that can take the anomaly detection, what's been detected as an anomaly, and identify what the root cause of that is. Then we take that to prognostics. In other words, identifying what the remaining useful life of the device or component is, and then moving towards mitigation. So here again, you can see that there's implicitly the notion of control coming in, right? And I mean control from the sense of the field of control theory, the idea of taking data, analyzing it, making a prediction, and then changing a behavior or changing some sort of an act based on that data. So we're thinking about it in this context for all of the connected devices that we're dealing with. Now it turns out that many of the connected devices don't give us the underlying application data. In the cars, we do get the underlying application data, but we don't get it, let's say, for the smart grid. We don't get it for alarm systems, for elevators, for vending machines and parking meters and all of those kinds of things. There, the data stays private, excuse me, to the underlying company. But in the cases that we do get the telemeter data, actually, let's say from cars, it becomes very interesting to look at it and look at it in this context. So now I'm going to branch a little bit into some of the algorithms that we've worked on. This is work that I and my team did at NASA. It's not been done yet at Verizon. We're considering this as one of the algorithms to do that anomaly detection. So this is now a transition away from what we've done exactly at Verizon or what we're planning to do to some more historical work at NASA. So one of the key issues that we face, both at Verizon as well as at NASA, and I think in many other applications, is that there are many different types of data. So there's a great deal of numeric data. Think about the cars, or in the NASA case, think about data coming off of airplanes. So all of the airplanes within the US, by and large, that are commercial transport aircraft have so-called FOQA data coming off of it. This is telemetered data, about 1,000 parameters coming at 1 hertz rate. And my team had built the capabilities to look at that data and look for anomalies, okay? And one of the key challenges was to deal with mixed data types. So we had continuous data. We also had discrete data. That corresponded to the switches that the pilots threw and throw during landing and descent, let's say, of an aircraft or during piloting and other operations. Text data, actual reports physically written by maintenance workers or written by safety personnel in the airline. Network data, the way the airplanes actually fly around in the US or abroad. So all of that data, in theory, should be used in order to determine whether or not a particular flight is anomalous or not. Frankly speaking, the same kind of data could be used to figure out if there's something anomalous with a car, right? You could take the continuous data off of, and discrete data off of the telemetered data off of that device. You could take text data, let's say from the safety reports off of NHTSA. You could take network data, in other words, how all the roads are connected, and tie it all together and do anomaly detection. Now, the way a lot of people would address this problem is you'd say, I'm going to build one anomaly detector for, let's say, the numeric type data, one for the text data, one for the network data, and somehow combine all of them. Instead, we took a very different approach. What we did is we took the approach of building a one-class support vector machine where the underlying kernel function was actually produced as a sum, a linear combination, of kernel machines, or kernel matrices, I should say. Each one is built off of a different data set. Okay? So notice that I've got a sum there. It says beta sub lambda times k superscript lambda. So lambda is going across the different data sets. So if you've got, let's say, 4 data sets, I think discrete, continuous, text, and network data, lambda goes from 1 to 4. You build a similarity matrix for each one of those things. You add them up. You could set all of the betas equal to 1, or 1 over lambda, or capital lambda, or something like that. But essentially, you could keep them all the same, or you could change the weights. You could say, I want to emphasize the continuous data more than the discrete data, or something like that. You form such a linear combination, and then you turn the one-class support vector machine crank, and what comes out of this thing are anomaly scores. And it's super interesting to look at these things. These anomaly scores are now tying together the discrete data, continuous data, all of the other data sets that I mentioned, and it'll give you a rank order of what the anomaly is and why the anomaly was called an anomaly, which, as you recall, is one of the key steps in building that system health management cascade that I mentioned earlier. So that's the direction that we took, and the fact is that it works beautifully. So I'll spend a little bit of time talking about this slide. So on the x-axis is the anomaly ranking. So to give you an idea of the kind of analysis we're doing here, we took data from a large number of aircraft. I guess it was several tens of thousands of aircraft. These are commercial aircraft that you and I fly on a daily basis. And we analyzed that data using the MCAT approach and not using the MCAT approach. So on the x-axis is the anomaly ranking. So the higher rank you are, the more anomalous the algorithm thinks you are. And then on the y-axis is the score. So what you see on the left-hand side is if you just use the numeric data, so you don't include text data at all, just use the numeric data, the anomalies that we knew about, which include things like flap speed exceedances, altitude deviations, unstable roll angles, and so forth, this is real data, what you see is that they're kind of really not that close to the lower left-hand corner. And you'd like them to be really close to the lower left-hand corner of the chart, right? But when you take the approach that we described, include the text data, and use all of the other information that was provided to the first set of algorithms, and remember the text data is literally reports that people wrote. And these reports say things like, I was coming in for a landing, the pilot. I was coming in for a landing at LAX, and I saw an aircraft on the runway ahead of me. So that's the nature of a report. Or a report could be, we were flying along, and there was an unruly passenger who started smoking in the lavatory. That's what these reports say. So you take all of that, you toss it into MCAD, and what happens is that the rankings change appreciably. This is a significant difference. If you look at the anomaly ranking is a log axis, and you can see it pushes them down much, much closer to the lower left-hand corner. And what we found through our analysis is this approach can really help in understanding what the nature of the anomalies are and how they work. And this is, I think, one of the best examples. And here I'm going to tie it back to the connected machines that I was talking about. So this is an example of a discovery from MCAD that occurred on a flight that was landing in Europe. And what happened on this particular flight is that the pilot lost understanding of what was going on the airplane. Okay? So what that means is that there's a flight management system. That's the automation that we all really are striving for. That autonomous system is coming in, bringing the airplane for a landing, and the pilot did not know what mode that plane was in, what the configuration of that plane was. And so the way they do it is they flip switches and they see, oh, if I flip this switch, how does the airplane behave? Oh, that's not what I expected, so let me put that one down and let me turn this one on. And they do this a few times, and you can see, if you look at the slide closely, you can see a lot of these events occurring in this auto landing configuration. And this was vetted by a large number of people in the airline industry, at NASA, and many other places, as one of the types of issues that can occur when a person loses a clear understanding of the nature of what's going on in automation. So now imagine that we have autonomous vehicles running on 101, and people are asked at various times to take control of their vehicle, and they're not paying attention. This type of analysis, in my opinion, is going to be very, very important. And the algorithms that support this kind of analysis is going to be very important in understanding how people are actually integrating and interacting with the vehicle. It poses a very unique challenge, and I think the data that we have going to help us understand that a little bit more. So I haven't gone into a great deal of detail about what this means. Let me just say that it's clearly identified as a key problem in the aviation domain. This is called pilot mode confusion, and it's a relatively common occurrence. And the question is, what's going to happen when the pilot is actually an individual driving their car, relatively unskilled individual driving their car, high-density traffic, 80 miles an hour on a freeway that you and I occupy. So let me stop there and see if there are any questions before I move on to the next section of the talk. How much time? I've got 5 minutes. Yeah, that's a really interesting question. So so the question was, in the formulation that I showed, are those betas learned or are they set by us? So the fact is they can be set by us, and we tested it, beta equals 1 over capital lambda, where capital lambda is the number of kernel matrices. But you can also learn it through two methods. You can do cross-validation, or you can tune it to what the expert wants to see. That's a little bit dangerous because experts, especially in the domains we were working with, feel that they already know what the problem is on the aircraft, and so they say, okay, we'll just turn up the volume on the continuous measurements, and we're going to find altitude deviations. And it's true you will, but what you end up losing are a lot of the things that they didn't know about. And so that's why we didn't really go in that direction all the time. Any other questions? Okay, so here's the picture. So I wanted to show you a picture of the connected devices that I mentioned earlier. These are also running in Mercedes cars. I think it's going to be a great data set to look at. Let me show you some of the real data that comes out of this telemetered system. So on the left-hand side, you can see Japanese cars. On the right-hand side, US cars. X-axis is total gallons consumed. Y-axis is miles traveled. It's just an incredible picture. Just 2 weeks ago, I presented this in Detroit. A whole bunch of car manufacturers were there. And it was very interesting to watch their faces as I put this slide up, because you can see that there's a certain segment here on the right-hand side of the picture where the cars are being driven, have a huge number of gallons consumed, and they go a relatively short distance. And it's a very clear segment. And I see smiles here, there. I saw a few concerned faces. The Japanese automakers were kind of a little bit more jubilant when they saw this picture. So if you take a look at this one, our Cadillacs are kind of down at the bottom end of the spectrum, Volkswagen's at the top. And there are many ways to look at this. One of the most amazing things about this particular data set is that you can look across virtually all makes and models of cars. And you can see things like this. So x-axis is year, y-axis is typical maximum speed. There's clearly a difference between the Honda driver and everyone else. And I didn't get a chance to talk to the Honda people, but I don't know if they know this type of information. And this is a very simple visualization, no big machine learning going on here. Super interesting to look at. But it gives us some insight into what might be happening on the roads. And I think from a machine learning standpoint, this is data that we can explore for various purposes. Any comments? So I'll leave you now with one last algorithm. And this gives you an idea of some of the directions that we're thinking about. A collaborator of mine and I submitted this paper, NIPS 2014. It's going to go on the archive probably today, if not sooner. The idea here is to say, if you're going to make a prediction, let's say for those Honda vehicles, about how those cars are actually performing with respect to fuel consumption, you might want to have a prediction interval. In other words, some bound of confidence that tells you how well your prediction is compared to what is actually going to happen. There are many ways of doing this in linear algorithms. Linear least squares algorithms can give you a confidence bound. But the problem is that those are fixed and they don't change with respect to the inputs. We developed a new method, which we call prediction interval estimation using bootstrap regression, that essentially does the following. It's a beautiful mapping, in my opinion, at least, to the MapReduce operations. Here, what it allows you to do is build a very large number of regressors at scale, aggregate the predictions of those, compute quantiles of their predictions, and we proved in this paper, at least we think we proved in this paper, that those quantiles will converge to the theoretical distribution of prediction intervals that are conditioned on the inputs. So it's really cool, and if you look at it, you can see that on real-world data, we applied this to data from aircraft in the paper that we submitted. What you can see here on the x-axis is time, y-axis is fuel consumption. This is not for cars, this is for an airplane. Those confidence bounds that are plotted in pink are actually the prediction intervals derived from the algorithm, and the blue line is the true value of fuel consumption, and we were able to detect that this particular airplane was actually burning more fuel than it should have, and it turned out that it was actually true. We actually went back all the way to the maintenance people, and it turned out that there was actually a problem on this airplane that they diagnosed using this method that they had never known before. So I'll conclude there. I thank you for your attention, all the questions, and I'll be around for further conversation.